Welcome back. In this lecture, we will formulate two more examples of linear programming formulations, problems. And both of these examples are simple examples, but they contain some special features. And you need to learn these special features. Basically, we will be talking about how can we linearize a min-max or max-min type objective function, and how can we linearize an absolute value with these two examples. So let's get started. Okay, let's formulate this example. In fact, this is a very simple example, but especially in part B, we will see a different feature of modeling. So in this problem, it said that in order to prevent excessive speed on the highways connecting Muscat to the surrounding cities, it's desired to determine the number of policemen to be placed on different regions of the highway. So we divide the highway into 8 different regions. Okay, so and for each region, there is a maximum number of policemen that we can assign. It means that for region 1, we can assign at most 4 policemen. For second region, we can assign at most 8 policemen. So this number here gives us the maximum number of policemen that we can assign to each region. And when we assign 1 policeman to this region 1, then there is a measure of prevention potential. So we want to prevent this excessive speed, and this is a measure for it. And 1 policeman in region 1 has a potential of prevention of 11. And this is in proportion with the number of policemen. So it means that if we assign 2 policemen, then this prevention potential will be 22. Okay, and for different regions, these numbers, these measures are different. And we have, at most, we can assign 25 policemen for all these regions. And the question has 2 parts. In the first part, we will formulate the problem in which we try to maximize the total potential of prevention by assigning the policemen to these regions and different regions of the highway. Okay, and it's a very simple formulation example. Let's do it, but the first thing in formulation is to define our decision variable. And in this example, the decision variable is very obvious. It's so obvious, and I will use this compact way of defining it. Okay, so you should from now on get used to it. Instead of saying that x1, x2, x3 and etc., I will just say xi here, I being the index. This will be the number of policemen assigned to region, highway region I. Again, as I said in previous lectures, if in your decision variable you have I index, then in your definition you should use I. Otherwise, there is a problem with it. Okay, so this is our decision variable. And part A of the question is very easy. We want to maximize the total prevention potential. So it will be a maximization, and starting from the first region, okay, the maximization potential, prevention potential is 11 for 1 policeman. So 11 times x1 will be the total potential of prevention in region 1, plus 3 times x2, which is the second in the second region, and you should write it up to the 8th region, which is 13 times x8. And again, this is just a simple summation which we can represent with a sigma notation. Okay, so basically it will be summation of I from 1 to 8 xi, but of course it is not just xi, but for each xi we are multiplying by these coefficients. So it means that we need to define these parameters of the problem. And again, what are the parameters of this problem? What is the input? So if this is LP, our LP model, these xi's are our decision variables. And what about the input of this model? So this potential prevention, this is one input. And you see this is for region 1, region 2, region 3, we have a different number. So it means that this parameter, I am going to represent it by P. P1 is 11, P2 is 3, P3 is 4. So all in all, I am going to define it as PI. Okay, this PI is the prevention potential. So this PI is an input into my model. But also, I know these numbers as well. What are these numbers? These are the maximum number of policemen that we can assign to each of these regions. And it's also an input. So it's also a parameter. Without solving, before solving the problem, I know these values. So again, I'm going to use a different notation. And for this one, I'm going to use, let's say, this value will be M1, maximum number of policemen. This value will be M2 and etc. So I'm going to define this as MI. Again, this I index represents the highway region. So PI and MI are the input of the model, and xi's are the output, the decision variable. After solving the model, we will learn them. So let's return back to our objective function. So our objective function basically will be the multiplication of this prevention potential by xi and summation over all indices. By the way, usually new learners of LP modeling make this mistake. In objective function, you see in the previous lecture we have seen that in constraints we write on the right hand side, for example, I from 1 to, let's say, 8. There is a constraint over here and we write to the right hand side as I from 1 to 8. And it means that you are repeating the same constraint 8 times with a different I index. In the first constraint, I takes the value of 1. And then you write the constraint again and I takes the value 2, and you do this 8 times. And as I said, some new learners do like this. They write the objective function and then in the objective function they write for all I or I from 1 to 8. Never and ever in an objective function you cannot have this I index here on the right hand side. The objective function is a single function. It should be a function. It is not, for example, when we write this in a constraint, it means that we are writing 8 different constraints. And if you write it like this here, it should be you are writing 8 different objective functions. It's meaningless. Okay? The objective function is a single function, and if you are writing this index to this right hand side, it is a mistake. Never do it. And also, if you have this I index, for example, you have written it as a summation, at the same time you cannot write it here. So I index will take its value from this summation. It will not take it from here. It cannot take the value from both sides, from 2 different places. So it is also a mistake. So learning how to write these objective functions and the constraints in a compact way is very important. So you need to understand what's going on when we write it in a specific way. And this is our objective function. Since we try to minimize, we try to maximize the total potential of prevention. And now our constraints subject to, basically we have one constraint stating that at each highway region we can assign a maximum number of policemen. So for the first region we can assign at most 4 policemen. And it's an easy constraint. Basically what we will do is this x1, which is the number of policemen assigned to highway region 1, and it should be less than or equal to 4. x2, highway region 2, number of policemen is in highway region 2, and it should be less than or equal to 8. And we should do this for all decision variables. This x8 should be less than or equal to 4 according to this table. But again, I don't like to write these constraints again and again, repeat the same constraints. So remember, this was M1, this was M2, and this was M8 according to my definition of this Mi parameter. Basically, what can I do? I can write this constraint as xi less than or equal to mi. And if you write it like this, the constraint is correct, but it is missing. So whenever you use an index in a constraint, then that index should be either in a summation, in a sigma term, or should be on the right hand side. And you should set the values of that index. So here, I'm not summing, I'm not writing this. Look, if I write it like this, I from 1 to 8, what exactly I'm writing? I'm writing x1 plus x2 plus up to x8. And I'm saying this is less than or equal to this mi. But my constraint, am I summing up these x values? No. That's why you cannot write it in sigma notation. In this case, I'm repeating the same constraint 8 times. It means that I'm writing this I from 1 to 8 to this right hand side. Or, as I said in the previous lecture, instead of writing this in this way, I can just write for all I, any one of these. Okay? So this is the first constraint, and the second constraint says that the total number of policemen that you can assign to these highway regions is 25. Okay, now I am talking about the total number of policemen. So how can I write that total number? Okay, the number of policemen that I am assigning to region 1 is x1. To region 2 is x2. Region 3 up to region 8. So this summation is the total number of policemen that I am assigning to all these highways. And this number should be less than or equal to 25. And this constraint is correct, but it is not in compact form. I'm going to write it in compact form, so it will be I from 1 to 8 xi, and this number will be less than or equal to 25. Okay, now let me ask you a question. How many constraints are there here? How many constraints did I write? If you say we have written only one constraint, then you are wrong. In this constraint, in fact, we have written 8 constraints. First one is x1 less than or equal to m1, x2 is less than or equal to m2 is the second one, and the last one is x8 less than or equal to m8. There are 8 constraints. Although you see only one equation here, this right hand side I from 1 to 8 tells you that there are 8 constraints there. How many constraints do I have here? Now I have only one constraint, single constraint. And what's that constraint? It is this one. Okay? Only one constraint. So it means that when I write this constraint in this way, in compact form, in total I have 8 plus 1, 9 constraints. Not more, not less. Okay? So you should be able to identify these as well. It is very important for your understanding. Okay, and also I'm going to write it here, this non-negativity constraints xi greater than or equal to 0 for all I. So this is the formulation of part A, the first part, and it's written in compact form. Again, this 25, you see, it's just a single number. And if you like, you can represent it as a parameter. And here we should write it, we should state it as a parameter of the problem, as an input of the problem. And what I am going to do it here, it is the 25, at most 25 policemen can be used. We will give a name to it. Just give a name. I am going to use A. Okay. This A is the maximum number of policemen that we can use. And as you see, there is no index on it. So if we don't have an index, it means that it is just a single number, which is 25. If we have a single index, it means that it is a vector. So it's a single dimensional variable. It's a single dimensional data, like here, 11, 3, 4, 14, and etc. Just a vector. If there are two indices, let's say we have a parameter bij, then this is a table, this is a matrix. There are two dimensions. I values represent the rows and j values represent the columns. If we have a parameter which has three indices, okay, b, I, j, k, then it means that it's a three-dimensional vector, three-dimensional array. Okay, you should understand, you should be aware of these things. And if we use this A notation for this maximum number of policemen, we can just replace this 25 with A. And when you look at this number over here, even this number, you see this number of regions, which is 8. We can also input it as a parameter into model. I'm going to use this R to represent the number of regions. Okay? And again, it's just a single number. And wherever I see 8, I can use that value R and R over here. And you see now in this model, in this compact form, there is no numeric values. All parameters and decision variables. And when you see such a model for the first time, how can you understand that this pi, is it a parameter or decision variable? What about this xi? What about this mi? Is it a decision variable or parameter? How can you identify it? So you don't know, you didn't model the problem, someone else modeled it and someone else gave it to you. And how can you understand if these notations are a parameter or a decision variable? Okay, for this purpose, just look at the non-negativity constraints. If we have written a non-negativity constraint, then it means that that notation is a decision variable. We never write these non-negativity constraints for parameters. We never write pi greater than or equal to 0. We never write mi greater than or equal to 0. We never write these. Because we already know their values. We know these mi's, we know these pi's. They can be negative, they can be positive. It's not important for us. We only want to determine the values of these xi's. Okay? So we understand if a notation is a decision variable or parameter by looking at these non-negativity constraints. If a notation is not listed there, it means that it's a parameter. But if it is listed there, then it's a decision variable. Okay, so this is the formulation of part A. Now, let's consider part B. What does it say here? It says that formulate the problem of maximizing the potential of the region having the minimum potential of prevention. Okay, we need to think about this a little bit. So let me clean this screen and we will continue. Now in part B, we changed our objective function, and now we are considering again maximizing the potential of prevention, but we are not trying to maximize the potential of prevention, the total potential of prevention, but we are now interested in the region which has the minimum potential of prevention, and we want to maximize it. So let me try to explain it like this. So assume that this is our highway. Okay, we divided it into regions. We have 8 regions. And assume that I decided to assign 2 policemen to here. It means that the potential of prevention is 2 times 11, 22 from here. And then I assigned, let's say, 5 policemen to here, to the second one. So the total potential of prevention here is 15. Then I have assigned, let's say, 4 policemen, so that we have 16 here. Then I have assigned 1 policeman to here, so we have 14, and etc. Now what do? We look at these preventions, potentials at each region, and we find its minimum value, which is this one, which is 14, and we want this minimum one to be as much as possible. Okay, so instead of having, let's say, in the previous solution, we were just interested in the total. So what can I do? For example, this has a potential of prevention of 14. So if I assign all 7 policemen to here, it will contribute to the total by 14 times 7, which will be 98. Okay, a total potential of prevention. But when I have 98 over here, then I may have this potential of prevention in the 5th region to be, let's say, only 2. And you see, although there is a good amount of potential in one region, the other region is very poor in this sense, and there may be, let's say, excessive speed in this region. So I don't want it. Instead of having 98 here and 2 here, for me it's better to have, let's say, 14 here and 14 here, so that the minimum potential is more. Okay, in the previous solution the minimum potential was 2, but in the second solution the minimum potential is 14. But when you look at the total prevention, in the first one it is 100 if we just consider only these 2 regions, and in the second one it's only 28. You see, although according to the previous objective function this solution is better, I don't like it because this region has a poor potential. So I want to maximize the potential of the region which has the minimum potential. Okay, now this is the idea, but how we can represent it in mathematics using mathematical formulas? Remember, our objective function is a mathematical formula. How can I write it? And maybe the first question, what about our decision variable? Shall I change my decision variable definition? And in fact, no, because we are still trying to decide on the same thing. What is that? We try to assign this policeman to these highway regions. So basically, my decision variable will be xi as the number of policemen assigned to highway region I, and this I goes 1 up to 8. Okay, now how can I write my objective function? First, let's try to identify the prevention potentials of each of these regions. So for region 1, if I assign x1 policeman, what is the prevention potential? It will be 11 times x1, right? And remember, in the previous case, we defined this as P1. So the prevention potential of region 1 is x1 times P1. Okay, what about region 2? It is x2 times P2. Region 3, it's x3 times P3. And for region 8, it's x8 times P8. Okay, then which one of these is the minimum? How can I find it? Basically, we will use the min formula. What's min formula? Remember, in Excel, in Java, in different programming languages, we have a function. We can represent it like this: minimum of x1 p1, x1 times p1, okay, x2 times p2, x3 times p3, and all the way up to x8 times p8. So this min over here, it is not the maximization or minimization. It's not the objective function. This whole is a function by itself. Okay, it's the function itself. And what does it give? It gives this. If this number is, let's say, 22, and this number is 14, this number is 16, and etc., and this number is, let's say, 8. So we are trying to find the minimum of these numbers, and the minimum is 8. So this min gives us the minimum of them. Okay, then what's our objective function? Our objective function is to maximize this minimum. Then how can we write it? Let me clean up some space. Basically, we are going to write it as maximize. So now this is our objective function, this max. And what we try to maximize? We try to maximize this minimum of, I will write P1 times x1, P2 times x2, and P8 times x8. I want to maximize this minimum of these elements. How many elements are there? 8 elements, 8 terms. Okay, so but you see this one here is not in compact form, and I don't like compact forms. We want to write them in compact form. And how can we write it? Basically, again, we can use this I index, and we can just say that maximize minimum of pi times xi. We represent in this way, and we just write here as I from 1 up to 8. Basically, this means that we are placing this I index from 1 up to 8 to the terms inside min, and we will obtain P1 times x1, P2 times x2, up to P8 times x8. And what's P1? From here, it's 11. And what's P2? It's 3. And what's P8? It's 13. And we want to maximize this minimum. Good. What about the constraints? Still, we have this maximum number of policemen. So we will have this xi less than or equal to mi for all I. What about the total number of policemen? So total number of policemen that you can use is still 25. It means that this xi, I from 1 to 8, this summation should be less than or equal to a, which is 25. These constraints are still the same. And of course, I have this xi greater than or equal to 0 for all I non-negativity constraints. Good. This is the formulation. Is that all? No. There is a problem here. And what is that problem? That problem is in this objective function. This objective function over here is not a linear function. You see, it is the function here is minimum of something. It's not linear. But the good thing is we can use a method to make this problem, to make this model linear. And how does it work? It works in this way. We define a new decision variable. New decision variable to represent this minimum function, this min function. And what do we say? Let the minimum element of these 8 terms, the minimum of these, be z. Okay, this z is another decision variable now. Then what we do in our objective function, we try to maximize this z. Instead of maximizing the minimum of something, we try to maximize z. But we need to add some constraints to satisfy. And what do we want? We want this. The minimum of these elements to be equal to z. So if, let's say, this is 15, if this is 8, this is 22, and the minimum of them is 8, I want the value of z to be 8. After solving the model, I want the value of z to be 8. If I just say maximize z, what will it be? It will be infinite. If there are no constraints, z value will be infinite. But I want its value to be equal to the minimum of them. And here we make this idea. What is that? If z is the minimum of these, which is 8, then z is less than or equal to this first one. Since z is minimum, it is either equal or less than this one, right? Because it's minimum. And z should be less than or equal to this second one as well. And z should be less than or equal to this last one as well. So since z is the minimum, it should be then less than or equal to all of them. So we write this as a constraint and say that z is less than or equal to p1 x1. Another constraint, it should be less than or equal to the second term up to z should be less than or equal to p3 x3. And remember, this is 15, this is 8, and this is 22. All the others are larger than 8. The minimum is 8. Let's assume the minimum term is 8. And then how can this, okay, our idea is correct, right? Our idea is correct. And if z is the minimum, then z will be less than or equal to all of them. But what do we want in the optimal solution? Optimal solution, we want the value of z to be equal to 8. So it cannot be 7, it cannot be 6. It should be equal to 8. And how do we guarantee it? And look at this part, look at this model over here. Let's assume that we have all these constraints and the optimal z value is equal to 7. Let's assume it. Can this be an optimal solution? Can optimal z value be equal to 7? No, because we can increase its value by 1, make it 8, and we still satisfy the first constraint, we still satisfy the second, we still satisfy all others and the last one. And 8 is larger than 7 for a maximization objective. It means that 8 is a better solution, so 7 cannot be optimal. And now the question is, okay, we can increase it by 1 more and make it 9. And what happens if it is 9? Let's see. We satisfy this constraint, but we cannot satisfy this constraint. It's violated, so 9 is not feasible. So it means that if we write the constraints in this way, in the optimal solution, we satisfy that z will be equal to the minimum of these. Okay, the idea behind this method lies in this logic. Okay, so what do? We define a new decision variable, and we set this decision variable to be equal to the minimum of these terms. And then what do we write? We keep the original objective, which is maximization, and say this max z subject to, we said that now this z will be less than or equal to, since it is the minimum, it will be less than or equal to all the terms inside the minimum function. Okay, so we write all these constraints. By the way, how can we write these constraints in a compact way? Let's write them. How do we write it? We say that this z is less than or equal to pi times xi for I from 1 up to 8. Okay, now our objective function and the constraints are these. And is this the whole model? No, of course not. We keep the original constraints. So still we have xi less than or equal to mi for all I. Still we have this summation I from 1 to 8 xi to be less than or equal to a. And we also have xi greater than or equal to 0 for all I. But remember, in this new model, z is also a decision variable, which means that we should have z greater than or equal to 0 as a non-negativity constraint. Okay, this is the model, and this is how we linearize. Look, in the original model, we have this model, max-min. It was not linear, but with some work, we could linearize it. Okay? And these type of functions are called max-min problems. And this linearization method is used, can be used for all types of max-min problems. In the same way, we just set this min a new decision variable and then write some additional constraints. On the other hand, in some cases, we may try to minimize maximum of something. Okay, so it may not be too meaningful for this model, but still, assume that we are trying to minimize the maximum prevention potential. In that case, we say minimize maximum of, okay, pi xi, I from 1 up to 8. In this case, still we can use linearization in a similar way. The idea is very similar, but you should be careful. Now, in the previous version, we said that this minimum is equal to z. But in this new version, we say that this maximum is equal to z. Okay? And our objective function becomes minimize z instead of maximize z. It will be minimize z. And the constraint now, look, in the previous one, the idea was this. If z is equal to the minimum, then it should be less than or equal to each of them. Now, here z is the maximum. So it means that it should be greater than or equal to each one of them. Okay, this is very important. You see the sign is different here and here. When it is max-min, so in this case it is max-min problem. When it's max-min, we should have less than or equal to. When it is min-max, then the sign is greater than or equal to, but never try to memorize it. Try to get the idea. If z is equal to the minimum, then it should be less than or equal to every one of them. If z is equal to maximum, it should be greater than or equal to every one of them. Okay, so although this problem is a very simple problem, the part B of the problem is very special in terms of this linearization, and you should learn this linearization. Let's solve another interesting example. This is also a very simple example, but again it contains some special feature that we need to learn. In this example, we have some data in a factory. This is related with the electric power used in the factory. Okay, this factory can work at different levels. Okay, if it works in level 2, then the electric power used is equal to 1 units. If we run the factory in level 3, then the power usage is 3. When it is 5, then the power usage is 3. When it is 7, then the power usage is 5. And we may have other levels. Okay, we may have level 4, 6, 8, 9, and etc. Different levels as well. And we want to find an equation. This is called regression. So that we want to find the relation between this level and power usage. And we assume that there is a linear type regression here, and somehow we can represent this power to be equal to some constant number plus some constant multiplied by this level. Okay, so these two numbers, beta 0 and beta 1, are the constants of this equation, but we don't know their values, and we want to find their values. And what will happen if we find the correct values? Let's assume that this beta 0 is 2, and let's assume that this beta 1 is equal to 0.5. So basically we will have this equation. This power will be equal to 2 plus 0.5 times this level. And if level is 2, we will just put 2 here, and we will make the calculation. 2 times 0.5, it is 1 plus 2, then the power will be equal to 3. But here you see it's 1. So it means that this beta 0 and beta 1 is not very good numbers, very good values. Okay? But still, we may not be able to find perfect values, so that for each level, when we input all of them one by one, we may not be able to find exactly these values. But what we try to do is try to determine this beta 0 and beta 1 values in such a way that whenever you use one of these levels, for example, you use level 2, and we should obtain as close as possible value to 1. Whenever we put this number 3, we should find the power usage from this equation as close as possible to 3. Again, with 5, it should be as close as possible to 3 again. And the thing is, how do we measure this closeness? Okay, again, in my formula, if it is 2 plus 0.5 times this level, and if we put input, let's say 2 over here, and we obtain power equal to 3. But the exact value should be 1. So 3 and 1, how can we measure the correctness? Okay, we say that this 3 minus 1 absolute value, okay, absolute value of this 3 minus 1 will be our measure. How close are we to the real numbers, okay, to the actual numbers. Again, when I input, for example, this 3 level 3 to here, I will obtain 1.5 plus 2, it will be 3.5, and the actual value is 3. So my closeness will be absolute value of 3.5 minus 3, which is 0.5. And here, from the first one, when I use it in my equation, I obtained closeness value 3 minus 1. And from the second one, I obtained 3.5 minus 3. Okay. And from the third one, again, I will obtain some value. And from the seventh one, I will obtain some value. And what I am trying to do is, I am trying to minimize this total deviation. We call it deviation, absolute deviation, from the actual values. Okay. So now we are going to formulate this problem. It is a very simple problem, again, with very small number of decision variables, but we should be careful about this problem. Okay, what's our decision variable? Please stop the video at this point and try to write our decision variable. Try to define it by yourself. And after thinking a few minutes on it, please continue the video. Okay, basically, if you think about this problem, what are we trying to do? In fact, we are trying to determine the values of beta 0 and beta 1. So these are our decision variables, in fact. Okay, so beta 0, which is the constant term of the equation, and beta 1 is the multiplier of the equation. If you like, you can use x1, x2. If you like, you can use x and y. But since in the equation we have beta 0, beta 1, we just say, we just define them as our decision variables. Okay, so beta 0 and beta 1 are our decision variables. What about the parameters of the problem? The parameters of the problem are given in this table. The levels and their corresponding power values are the parameters of this problem. Okay. But for this one, since there are only 4 values, 4 levels and 4 power values, I will not define a notation for these parameters. Okay, let's try to write our objective function. What is our objective function? As I have written it here, I want to minimize this value. And what's that value? Remember, what is this 3 over here? It is the value that I obtained when I insert this 2 into this equation. Okay, so I assume that this beta 0 was 2 and beta 1 was equal to 0.5, and when I insert here 2, I obtain this 3. So in fact, what I am trying to do is, I am trying to minimize this absolute value. So input just 2 here, it will be beta 0 plus beta 1 times 2, and this is the value that we obtained from this equation, and minus 1 is the actual value, and this is in absolute value. Then plus for the second level over here, again insert, this time we are inserting 3 to here. So we have another absolute value, beta 0 plus beta 1 times 3 minus the actual value is 3. Okay, then plus we insert here 5, and we have beta 0 plus beta 1 times 5 minus the actual value 3, and plus when we insert 7, beta 0 plus beta 1 times 7 minus 5. Okay? And we try to minimize this total deviation from the total absolute deviation from the actual values. Okay? And what are our constraints? Are there any constraints? Here it's said that beta 0 and beta 1 cannot take negative values. So it means that we have this constraint, non-negativity constraints. What else? Okay, no other constraints at all, and this is the model. But again, we should be careful with this model, because here in this model, in the objective function, we have these absolute values. And absolute value is not linear again. And it means that we have to somehow linearize, again maybe using a similar idea with the previous one. We need to linearize these absolute values. So let me clean the screen and we can do this linearization. Before linearizing this whole function, let's consider a more simple case, and let's assume that our objective function is this: minimize absolute value of, let's say, x minus some number 5. Let's assume that our objective function is this. Okay, so how can we linearize this? Basically, you can think about this absolute value x minus 5. There are two different ways of linearizing this. I'm going to show both of them. The first one is very easy. We will just use the previous idea. And in fact, what is this absolute value x minus 5 equal to? We can say that this is equal to maximum of x minus 5 and minus x minus 5. Okay? Why is that so? Let's assume that this term over here is 5. Then it is maximum of 5 and minus 5. And the maximum of 5 and minus 5 is equal to 5. Right? Assume this absolute value, this x minus 5, is equal to minus 5. Okay? And then from absolute value, we obtain 5. And in my max term, what do I have? Maximum of x minus 5, which is minus 5, and minus x minus 5, it is 5. And the maximum of these is again 5. As you see, if inside this absolute value, if it is positive, then from this first term here, we got the same thing. If it is negative, then from the second term over here, again we got the same thing. Okay, so instead of this absolute value, in fact we can use this maximum. So this is equal to minimum of, or minimize maximum of x minus 5 and minus x minus 5. Okay, there are just two terms over here, and as we talked in the previous problem, we can linearize this by just setting this value equal to another decision variable, which is z, and we say minimize z subject to, and since z is equal to the maximum of this, it means that z should be greater than or equal to all of them. Since it is maximum, it should be higher, it should be larger than all of them. So z is greater than or equal to x minus 5, and z is greater than or equal to this minus x minus 5. Of course, you can open this parenthesis, and this is basically our linearization. Okay, this is the first way. Let me write it here, first alternative. A second way to linearize this absolute value here is minimize x minus 5. Now what do we do? In fact, for this absolute value, this time instead of defining a single variable like z, we define two decision variables. Okay, we can call them let's say z and y. Okay, and what do? We set this we say this minimize z plus y. Instead of absolute value, we say minimize z plus y, and subject to, again we need to write a constraint, and this constraint is basically this x minus 5, we set it equal to, okay, z minus y. Okay, why is it z minus y? Can we write y minus z? Yes, you can write y minus z as well, but the thing is, in the constraint it should be one decision variable minus the other one, but in the objective function it should be the summation of these two decision variables. And how does it work? Let's talk a little bit on how does it work. So assume that this x minus 5 is equal to, let's say, 8. So what does it mean? Its absolute value will also be equal to 8. Okay, then over here we have 8 equal to z minus y. So it tells me that find, by the way, this here z and y are both greater than or equal to 0. Find two positive variables such that their difference is equal to 8. And you can find many alternatives, right? For example, 12 minus 4 is equal to 8. For example, 11 minus 3 is equal to 8. For example, 15 minus 7 is equal to 8. All of them are equal to 8. For example, 8 minus 0 is equal to 8. Is that right? Yes. Okay, then let's have a look at this objective function. It says that, okay, find two decision variables z plus y such that z and y such that their summation is minimum. Okay, for example, if we use 12 and 4 for z and y, then their summation will be equal to 16. If we use 11 and 3, then their summation will be 14. If we use 15 and 7, then their summation will be 22. But if we use 8 and 0, then their summation will be equal to 8. So this formulation is minimized when one of these decision variables is 0. Otherwise, it will be large, it will take a larger value, and the objective function tries to minimize it. So what happens? The idea is this: if we use, let's say, this formulation in this way, then if x minus 5 is equal to a positive value, so that absolute value is also equal to this, then here when we take z minus y, y value will be equal to 0 and z value will be equal to this absolute value, so that this z plus y will be equal to absolute value, and it is the minimum possible value. Okay. On the other hand, if this x minus 5 equals to minus 8, let's consider this time, if it is equal to minus 8, then the absolute value will be equal to plus 8, right? And here we will have this inside minus 8 equals to z minus y. And again the question is, find me two values, two decision variables z and y, such that its difference is equal to, their difference is equal to minus 8. And again, you can find a lot of alternatives. For example, 4 minus 12 is equal to minus 8. 7 minus 15 is equal to minus 8. And 0 minus 8 also equals to minus 8. And when you look at the objective function, we want to minimize z plus y. So here z is 4, y is 12, and z plus y is 16. 7 and 15, so their summation is 22. 0 and 8, and their summation is 8. Again, the same idea in a similar way. This time, since x minus 5, the term inside absolute value is negative, as you see this time, this first one became equal to 0, and the second one became equal to 8, so that minus 8 equals to minus 8. And this objective function is 0 plus 8, because z and y should be greater than or equal to 0. And this is equal to the absolute value itself, and it's the minimum possible value. You see, different than this first alternative. In the first alternative, we just defined single decision variable, but we have written two constraints. But on the other hand, in this method, we define two decision variables. But let me write the final version. X minus 5 equals to z minus y. So we defined two decision variables, and we wrote just a single constraint, and both of them works correctly. Both of them finds the correct value. Okay. In some books, instead of here z and y, what you will see is z plus, they call, and z minus. And why do they use it? Because this z plus becomes equal to the term inside the absolute value when it is positive. When this x minus 5 equals to 8, then this z plus becomes equal to 8, and z minus becomes equal to 0. And when this is minus 8, then z plus becomes 0, and z minus, the negative term, becomes equal to 8. That's why they, instead of using z and y, they use z plus and z minus. But of course, in Simplex, writing these superscript plus and minus is difficult, but it is just a name. Don't be confused. You can use x and y. You can use such z plus and z minus. It's not that important. This is just a name. Okay, but the final linearization is this. Okay, so now we learned how to linearize this absolute value. But remember, in our problem, we had this. Let me try to write it here. Minimize this absolute value, beta 0 times plus beta 1 times 2 minus 1 plus beta 0, beta 1 times 3 minus 3, beta 0, beta 1 times 5 minus 3, all in absolute value. And finally, beta 0, beta 1 times 7 minus 5. Okay, we want to minimize this whole summation. And in this whole summation, we have one absolute value here, another absolute value, another absolute, and another absolute value. And in these type of linearizations, we need to linearize each one of them separately. So in this version, we had just a single absolute value, and we linearized only that one. But here we have 4 absolute values, and we need to linearize all of them. You can use both versions, this one and this one. I'm going to use this first alternative and leave the second alternative to you. Please do it by yourself. Okay, try to use this second alternative to linearize this one, as I will show you. for the first alternative. So what we are going to do is, now I am going to define a decision variable for this one. But if you say, okay, this is z, this is also z, this is also z, and this is also z, it's not correct because they are different terms. It means that this first one should be z1, the second one should be z2, this should be z3, and this should be z4. They are different from each other. Then the objective function becomes minimize z1 plus z2 plus z3 plus z4. And subject to, okay, we will think them separately. For this first one, since z1 is equal to, according to this first representation, since z1 is equal to the maximum of them, it means that z1 should be greater than or equal to, okay, beta 0 plus beta 1 times 2 minus 1. And also z1 should be greater than or equal to negative of this, minus 1. Okay, these are the constraints related with the first absolute value. Now for the second absolute value, I will continue here. This z2 should be greater than or equal to beta 0, beta 1 times 3 minus 3. And z2 should be greater than or equal to negative beta 0 plus beta 1 times 3 minus 3. And we do the same thing for all others. Okay, can we write these in compact forms? Okay, for writing these in compact forms, we need to define these parameters. Remember, these 2, these 3, these represent the levels. And for these, I am going to define parameter L. Okay, I will write it as, this is L1, this is L2, level 2, level 3, and level 4. And these ones over here and 3 over here, they are the power values. So I'm going to say this is power 1, this is power 2, and this is power 3. Okay, so using these, now what do I have? And look, here I have Z1 for level 1 and for power 1, Z2 level 2 and power 2, and it goes in this way. Therefore, what can I do? I can use this index I and write Zi should be greater than or equal to beta 0 plus beta 1 times L1 minus power, sorry, not L1, Li minus Pi, and this is for I 1 up to 4. Why it is 4? Because we have 4 absolute values, 4 z's, z1, z2, z3, z4. And for each one of them I have this, and also this zi should be greater than or equal to negative of this, beta 0 plus beta 1 times Li minus Pi. Again, I from 1 up to 4. So in total, also I have this beta 0 greater than or equal to 0 and beta 1 greater than or equal to 0. Okay, so this is the linearization. And how many constraints did I write in this model? I have 4 constraints here plus 4 constraints here, so 8 constraints here plus 2 non-negativity constraints. You can say, should we write Zi greater than or equal to 0? But in fact, no, we cannot write it. We already wrote this Zi to be greater than or equal to these values. But the thing is, in fact, since this is absolute value, yes, definitely this Zi's will be greater than or equal to 0. So we can write Zi greater than or equal to 0 for this case, but, and for all I. But for a regular min-max problem, min-max of something, if we replace this by z and say this minimize z subject to z is greater than or equal to these terms, if all the terms inside this max is negative, then this z should be also negative. So in those cases, you cannot write z greater than or equal to 0. It will be a mistake. Okay, so be careful about this. So for min-max or max-min linearizations, the artificial variable, the additional variable that we use may not be greater than or equal to 0. Be careful. Okay, so this is how we linearize this absolute value using the first alternative. Now it's your turn to repeat it with the second alternative and also try to write it in a compact form. Okay, so this is the end of this lecture and this is the end of modeling examples. Now it's time to learn how to solve it. In the next lecture, we will start learning the simplex algorithm.